For the rest of Chapter 7, we're going to talk about breaking the octet rule. And before we do that, I want to talk about what kind of ideas of molecular stability that we've been using and how we can kind of think about what it means to break some of these rules that we've used to describe molecules. And so the octet rule has exceptions. This is a rule, it's not a scientific law, so it's just a guide. It is a useful rule, and we've seen it before. And so we're going to spend a lot of time talking about a lot of exceptions. That's not to necessarily imply that these are common. Most of the molecules that exist, that we use, that you're made out of, that the things that you touch are made out of, follow the octet rule. But there are molecules, there are atoms inside molecules that don't follow the octet rule. And there's a couple different reasons. You can have more than 8 electrons, you can have less than 8 electrons. You can have also a slightly different situation where an atom has an odd number of electrons associated with it. And so we're going to talk through these and look at how they kind of function. And so there is one kind of gimmicky exception to the octet rule, and that's hydrogen. Right? Hydrogen only has 2 electrons in a valence, and its valence in a molecule. And you know, the thing is, this follows not the letter of the octet rule, but at least the spirit of the octet rule, the idea that your atoms want to look like noble gases. And so that leads to 2 electrons, it looks like helium. So it does follow kind of the idea, but I just want to use this as an example to show that the octet rule isn't necessarily like a Bible. You can break it, it's just kind of a guide that atoms tend to follow when they're taking on, stable configurations within molecules. They want to have 8 valence electrons, but just because something breaks that doesn't mean it's necessarily like forbidden or anything like that. When we do talk about the octet rule, we say that that tends to correspond to stable molecules. And when we use that word stable, literally all that means is that the molecule doesn't fall apart. A molecule that is stable means that the atoms don't fall apart into like individual fragments. Bonds don't just spontaneously break. And so we're saying that this is how, if these atoms were to come together, this is how they would arrange in a way that leads to them not falling apart. And when we're talking about choosing a resonance, like a Lewis structure, like picking major structures and resonance and all these ideas, what we're trying to do is come up with a model that reflects that, how those atoms are arranged. But just because a molecule is stable, which again just means it doesn't fall apart on its own, that doesn't mean it's not reactive. If you introduce that molecule to, say, a different molecule, they could very much react and change into something else. So, for example, ammonia, NH3, and HCl, when by themselves, they are perfectly stable. They don't fall apart into the atoms. But if they come into contact with each other, they will very quickly react. And you will get ammonium, a cation, and chloride, an anion. And so they will very quickly, those atoms will rearrange. So a lot of the questions, we can kind of return to the ideas of like, why is NH4 NH4 plus? Why is ammonium a polyatomic ion? That is a relatively stable arrangement of nitrogen and hydrogen atoms. And if you go positive, if it loses this electron to the chloride, you end up with an octet around the nitrogen. So the reason why you make ammonium is because it's what's the most stable arrangement when you have NH4 and something else, in this case a chlorine, to take that extra electron. So what is the most stable arrangement is going to depend on what you have available. Molecules being stable just means they don't fall apart. Molecules will react based on what other atoms are present, and then you can get different sorts of setups. So we're going to talk about molecules that exist as we move through our discussions of octet rule exceptions. These molecules are stable. It doesn't mean they're not reactive. And we're going to talk about some of that reactivity and some of those implications and how we can understand that reactivity based off why and how those molecules show exceptions to the octet rule. I also want to quickly touch on another idea with respect to, say, stability and reactivity. Chlorine is an extremely reactive element. It's also a stable molecule. It forms Cl2 molecules. They don't fall apart into chlorine atoms, right? It's a diatomic. The atoms actually prefer to be in the molecules. And so chlorine, you can look it up and you can find all sorts of dangers of chlorine and when handling chlorine. Just because chlorine as an element is reactive and unsafe doesn't mean that chlorine atoms always are. When chlorine atoms get into, say, different compounds, they become much more stable. Sodium chloride table salt is extremely unreactive. It is really hard to get that to do any sort of chemical reactivity. So chlorine reactivity is not an inherent attribute of chlorine atoms. Chlorine atoms in a molecule with only other chlorine atoms are very reactive. But once they go to being that chloride ion, they're inherently different, right? They're inherently different and they're much more stable. They're much more stable. There's this anion, they've gained that extra electron. You have the electron affinity that's been that extra energy gain is why they're more stable. And so they don't really react there. So when we start to talk about reactivity, we really need to be focusing in on what is the compound that it's in? What is the state that it's in? Chlorine as an element, very reactive. Chlorine as an atom in a different molecule, not necessarily very reactive. And in fact, in a lot of molecules, chloride is extremely stable. Okay, no questions for participation 626. We're slowing down. Pace is slowing down a little bit. Got a couple more videos left. See you in the next one.